Hello students, good evening to all of you. In this video, I am going to discuss the retrosynthetic analysis and its synthesis of the given compound. Now let us read the question first. Propose a retrosynthetic analysis of a compound. Your answer should include both the synthons showing your thinking and the reagents that would be employed in the actual synthesis. Okay, this is the molecule that is given to us. So this is our target molecule. So this is what we call it as a target molecule. And then if we observe carefully, see TM in the sense this is target molecule. Once if we go through the molecule carefully, this given target molecule is nothing but an alpha beta unsaturated ketone. This is an alpha beta unsaturated ketone. So we know that the alpha beta unsaturated aldehydes or alpha beta unsaturated ketones are synthesized by using aldol condensation. So therefore, in this particular reaction, if we want to get an alpha beta unsaturated carbonyl compound, alpha beta unsaturated carbonyl compound is obtained from a beta hydroxy carbonyl compound. So you need to have a beta hydroxy carbonyl compound. Beta hydroxy carbonyl compound. And then now this disconnection, see, aldol disconnections are what we call it as 1,3 di-O. 1,3 di-O, this is 1, this is 2, this is 3. On first carbon as well as on the third carbon, you have an oxygen, so it is called 1,3 di-O. So this is nothing but an aldol disconnection. Aldol disconnection. So this is aldol disconnection. In the aldol disconnections, as we know very clearly that the CC bond is formed between the alpha and the beta carbons. So this is alpha, this is beta. So therefore, the CC bond is always formed between alpha and beta. So we have to disconnect between alpha and beta. So once you disconnect between alpha and beta, then we'll get the synthons. So what are the synthons we are getting? We are getting this is OH plus and then minus CH2 minus CH2 C double bond O CH2. So these are the synthons. These are the synthons. This is what we call it as an A1 synthon. And this is what we call it as a D2 synthon. So the synthetic equivalent for this is cyclohexanone. And the synthetic equivalent for this is the saturated compound, just to saturate this. So this is a 2-pentanone. Now this is an aldol condensation between the cyclohexanone and then 2-pentanone. Now let us go to the synthesis of this reaction. We can also synthesize this 2-pentanone by different methods. So I will explain you the synthesis of 2-pentanone at the end of this video. Now let us write down. So this is what is called a retrosynthetic analysis. This is retrosynthetic analysis. And these are all the synthons and synthetic equivalents. Cyclohexanone is one synthetic equivalent, and the 2-pentanone is another synthetic equivalent. Okay, now let us go to the synthesis of this reaction. Synthesis is like this. What we need here in this particular reaction is that we want a less substituted enolate. This is 2-pentanone. 1, 1, 2, 3, 4, and then 5. So therefore, we want a less. Now this lesser substituted enolate is formed by treating with LDA, lithium diisopropylamide. So here we have H. So this is LDA ion. So we'll get O minus double bond CH2. So this is a less substituted enolate ion. So less substituted enolate ion is less substituted enolate ion. So less substituted enolate ion is always obtained by treating with lithium diisopropyl amide. So LDA is nothing but lithium diisopropyl amide. So this is the structure of LDA, N minus, Li plus, diisopropyl, a sterically hindered base. So this is the structure of your LDA. And now we have to write down the aldol condensation between this less substituted anion and then the cyclohexanone. Cyclohexanone plus O minus enolate ion 1, 2, 3. So therefore this undergoes aldol condensation. This is enolate ion, which is less substituted. Now, this, we know that in aldol condensation, it undergoes nucleophilic. The first step is nothing but the nucleophilic addition reaction. This is a nucleophilic addition reaction. And then this undergoes a nucleophilic addition reaction, and this is nothing but aldol condensation. So here we have, this is O minus, CH2, C double bond O, CH2, CH2, CH3. And then this is the new carbon-carbon bond formed. This is the new CC bond formed. Now this on hydrolysis, protonation. Then we'll get the beta hydroxycarbonyl compound. So this is beta hydroxycarbonyl compound. This is beta hydroxycarbonyl compound. So, and then remember that this is nothing but the new carbon-carbon bond formed. That is the new CC bond. New CC bond formed. Okay. The next step is nothing but a dehydration step. So therefore, the dehydration step can be carried out either in the presence of an acid medium or in the presence of a basic medium. We can do in any medium. So let us suppose you are using acid medium here. So just protonate this. So once you protonate it, then you'll get OH2 plus, OH2 plus, and then so this is now this undergoes loss of H plus as well as water molecule. Minus H2O as well as minus H plus. Now that lead to the formation of alpha beta unsaturated carbonyl compound, the required alpha beta unsaturated carbonyl compound. So we have got the target molecule. Over. The synthesis is over. So this is a very simple one. Alpha beta unsaturated carbonyl compound. Very simple and very interesting reaction this is. So this is a dehydration step. Dehydration step. Okay. Now here I will tell you how to synthesize this 2-pentanone. I'll give you two methods just to enjoy the chemistry. Synthesis of 2-pentanone. 2-pentanone is commercially available, but I'm just giving you the synthetic method of 2-pentanone. See here, this is RSA, this is retrosynthetic analysis. Number one, retrosynthetic analysis. So this is 1, 2, 3, 4, 5. This is 2-pentanone. This is no target molecule. Now, if you want to get a 2-pentanone, now then 2-pentanone is obtained by, see here you need to have OH, 2-butanol. This is 2-butanol. So this is what we call it as an FGI oxidation. Functional group interconversion oxidation. Okay then, next. This 2-butanol is a secondary alcohol. Now this secondary alcohol is obtained by, so this Grignard reactions, this is called 1,1-CC disconnections. 1,1-CC disconnection. CC 1,1-CC disconnection. So this is 1,1-CC disconnection. In the sense, see, we know that the secondary alcohols are obtained by the reaction of an aldehyde other than formaldehyde with a particular Grignard reagent followed by hydrolysis. So therefore, what I have to do is that here I will disconnect the molecule here. So then the synthones are like this. This is CH3CHOH plus. This is A1 synthon. Plus we have CH2, CH2, CH3. CH2, CH2, CH3 minus. Now this is A1 synthon. And then the synthetic equivalent for this is acetaldehyde. And the synthetic equivalent for this is 1, 2, 3, propyl magnesium bromide. Now this is the synthesis. Now what you need to do is that what you need to do is that you take acetaldehyde plus treat this with magnesium bromide. 1, 2, 3, propyl magnesium bromide. We know that metals are electropositive, and then the alkyl group acts as a nucleophile. So this is a nucleophilic addition. A nucleophilic addition. And then so this is CH3CO minus CH2, CH2, CH3. O minus MgBr plus. This is new CC bond formed. New CC bond. And then this on hydrolysis. You will get OH, CH2, CH2, CH3. So this is 1, 2, 3, 4, 5. So this is 2-pentanol. Now this is a secondary alcohol. And we know that secondary alcohol on oxidation with the PCC gives rise to the ketone. So 2-pentanone. So this is 2-pentanone is obtained. 2-pentanone is formed. Very simple and very interesting. I'll give you another method for the synthesis of 2-pentanone. See, this is CH3, C double bond O, CH2, CH2, CH3. Now, if we disconnect the molecule here, then we'll get CH3, C double bond O, CH2 minus, and CH3, CH2 plus. Now, the synthetic equivalent for this is called D2-synthon. D2-synthon, this is A1. So the synthetic equivalent for this D2-synthon is nothing but your ethyl acetoacetate, CH3, C double bond, CH2, C double bond, OET. Ethyl acetoacetate. And then the synthetic equivalent for this is CH3, CH2Br. Ethyl acetoacetate is what we call it as a beta ketoester. This is a very useful chemistry. Ethyl acetoacetate chemistry is very wonderful and very useful chemistry. Okay, then next one. So how to do the synthesis of this? Now this is RSA, this is the target molecule. This is RSA. RSA means retrosynthetic analysis. And now we'll go to the synthesis. See, this is CH3, C double bond O, CH2, C double bond O, OET, ethyl acetoacetate. This is EAA. And we know that this is an active methylene group, and this particular proton is acidic in nature. This particular proton is highly acidic in nature. So this proton is removed by treating with sodium ethoxide. Now this gives rise to CH minus C double bond O OET. Now this is now treated with your C2H5Br, Br, CH2, CH3. Ethyl bromide. Ethyl bromide, and then this is nothing but an SN2 reaction. This is your ethyl bromide. SN2 reaction. So CH3, C double bond O, CH, C double bond O, OET, and then this is CH2, CH3. Now what we need to do now is that we have to remove this ester group. So for that, first OH minus comma H2O. See, whenever you have an ester, RC double bond O, C2H5, once you heat with this with the NaOH, okay, now this becomes RC double bond O minus Na plus will get ethanol. Ethanol will be distilled out, and sodium salt on hydrolysis with an acid will get acid. So OH minus H2O and then followed by H3O plus. Now that turns out C double bond of OET into C double bond O, CH2, CH3, and then this becomes C double bond of OH. Now this is nothing but alpha and this is beta. So this is a beta keto acid. Now this beta keto acid on heating, it undergoes decarbonylation very easily. So minus CO2 will give you CH3, C double bond O, and then this becomes CH2. This is CH2, CH3. So this is 2-pentanone. Over. Now I'll ask you one question. Please write in the comment box. How do you synthesize ethyl acetate? By which name reaction you can synthesize as ethyl acetate? So please read the mechanism of this, name of the reaction and also the mechanism of the reaction. This is very, very important. So this is the second method. Now I'll tell you the third method also for the synthesis of 2-pentanone. So this 2-pentanone is very interesting. So this is 1, 2, 3, 4, 5. So this is the third method. This is the third method. So this is 2-pentanone, which is our target molecule. 2-pentanone. This is TM. Now what I will do is that I'll just disconnect here. Once you disconnect here, then what you'll get here? CH3 C double bond O minus. This is minus. And CH3 CH2 CH2 plus. See, this is D1 synthon. And this is an acceptor synthon. Acceptor synthon. So the D1 synthon synthetic equivalent will be your substituted dithiene. Substituted dithiene. And then the synthetic equivalent for this will be 1, 2, 3 propyl bromide. This is also a very interesting synthesis. Now this is retrosynthetic analysis, RSA. Now I'll give you the synthesis. Okay. The synthetic part is like this. This is CH3 C double bond O. So the synthesis will start with the dithiene. And then we know that this is weakly acidic proton. So you need to abstract this particular proton by treating with the N-butyl lithium. Treat with N-butyl lithium and then abstract this proton. Then we'll get an anion. A lithium salt, of course, it is called an anion. So C minus Li plus here, of course. Now this is now alkylated with propyl bromide. This is propyl bromide. And this undergoes an SN2 reaction. SN2 reaction. It is simply an alkylation. Yes, yes. Diethane chemistry is very interesting chemistry. See, this is CH3, and then this is the new CC bond that is formed. CH3, CH2, CH3. Okay then. Now, so therefore this is now alkylation is over. Now this is now hydrolyzed by using aqueous mercury chloride solution. So then this will be hydrolyzed. You can also write down the mechanism for hydrolysis. CH3 C double bond O CH2 CH2 CH3. So this is the new CC bond formed. This is the new CC bond formed. There is another method is also there for this 2-pentanone. See how the chemistry, you can enjoy the chemistry like anything. Once you know the fundamentals, you can enjoy the chemistry. Suppose if you go to any interviews, then you can explain all these methods. This is the target molecule. Now I'll disconnect here. I'll disconnect here. See, this is 1, this is 2, this is 3. So once I disconnect at that particular place, C double bond O, see here, I'll get a positive charge and then CH3 minus. Now the this is called A3 synthon. A3 synthon. The synthetic equivalent for this is alpha beta unsaturated carbonyl compound. And the synthetic equivalent for this is dimethyl lithium cuprate. So this is how you can do this. Now the synthesis is very easy. This is synthesis. Now you start with alpha beta unsaturated carbonyl compound. So this is called MVK, methyl vinyl ketone. This is another interesting compound, methyl vinyl ketone. We have so much of beautiful chemistry is there with methyl vinyl ketone. You can play like a football with this methyl vinyl ketone. You can do so many interesting conversions from this methyl vinyl ketone. Methyl vinyl ketone, take this methyl vinyl ketone, and then you have dimethyl lithium cuprate here. CS3 twice CuLi. That means this is Cu minus, and then this is CH3, and then this is CH3, and this is Li plus. So this is what we call it as a Michael addition. This is simply a Michael addition reaction. Or we can also call it as conjugate addition. So CO minus double bond CH2, and then this is the new sigma bond that is formed. And then followed by hydrolysis, and then tautomerization. This is OH, double bond, tautomerizes to 2-pentanone. This is 2-pentanone. This is enol form, and this is the keto form. So this is how you can synthesize this 2-pentanone in 4 different methods. See, please enjoy the chemistry, chemistry involved in this particular reaction. And after this, we'll go to another simple question. Write the retrosynthetic analysis, write down the retrosynthetic analysis And for the following compound, and write the synthesis with appropriate reagents, and write the synthesis with the appropriate reagents. This is question number 10. Okay. Now, what is the molecule that is given to us? The molecule that is given to us is this. This is very simple. See, this is the target molecule that is given to us. And if you observe carefully, this molecule is nothing but a tertiary alcohol. It is a 3-0 alcohol. And we know that tertiary alcohol is formed by the reaction of a ketone plus a Grignard reagent, ketone plus a Grignard reagent, ketone plus a Grignard reagent followed by hydrolysis. Gives tertiary alcohol. So it is very easy to synthesize this, and all Grignard reaction disconnections are called 1,1-CC disconnections. So what I will do now here is that I'll just disconnect here. And here I have OH. I'll get a positive charge here. And then I have CH3 minus. This is acceptor A1 synthon. This is a donor synthon. Now, the synthetic equivalent for this is this. That's it. So this is the ketone. Okay, a symmetrical ketone. And then the synthetic equivalent for this CH3 minus is that CH3MgBr. So this is synthesis is very easy. This is your retrosynthetic analysis, RSA. This is RSA, retrosynthetic analysis. And now we'll write down the synthesis. We'll write down the synthesis for this. CH2, 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 isopropyl, CH2, CH2, C double bond O, again CH2, CH2, isopropyl. So this is a Grignard reagent, CH3, MgBr. This is delta plus and this is delta minus. Now this undergoes nucleophilic addition. A nucleophilic addition takes place followed by hydrolysis. A nucleophilic addition followed by hydrolysis. This is O minus, this is CH3, again CH2, 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 1, 2. This is O minus MgBr plus. Now this on hydrolysis we'll get the target molecule over. This is OH, this is CH3. So this is the target molecule. And of course, we can also write down the synthesis of this ketone. That is not necessary. But anyhow, let us, just to learn the chemistry, we'll discuss about the synthesis of this ketone. So this is the final TM that is given. So this is 1,1-cc disconnect. Grignard reaction disconnections are all called 1,1-cc disconnections. And then synthesis of this ketone. Two CH2s, two CH2s. Oh, one carbon extra. Yes. So this can be easily done by, this is the synthesis of this. Now, if you wanted, this is the target molecule. If you want to write the RSEF for this retrosynthetic analysis, just disconnect here as well as disconnect here. So the synthons will be, this is C double bond O minus minus. That means, and then we have, this is the positive charge here we have. So this synthetic equivalent for this is nothing but your dithiene, 1,3-dithiene. See how interesting the chemistry of 1,3-dithiene is. This is CS2Br. So this is nothing but isobutyl bromide. Isobutyl bromide over. This is very easy. So synthesis is like this. This is synthesis is like this. This is dithiene. The proton is weakly acidic. This is weakly acidic proton. And then that weakly acidic proton is abstracted by treating with n-butyl lithium. Yes. Minus, and then treat this with isobutyl bromide. Isobutyl bromide. This is an SN2 reaction. This is the new CC bond formed, CH2, CH2. Similarly, repeat the same reaction with another mole of n-butyl lithium. Another mole of n-butyl lithium. The same reaction is repeated. CH2, CH2. Again, repeat the same reaction with another isobutyl bromide. In SN2 reaction. CH2, CH2. Isobutyl. CH2, CH2. Isobutyl. Now finally, see, these are the two carbon-carbon bonds that are formed. Two CC bonds are formed. So this is the first CC bond formed. And then this is the second CC bond formed. So this is now hydrolyzed by using aqua solution of mercury chloride solution. So then I'll get This is my target molecule. So thank you very much. We'll discuss some more interesting chemistry in the next video. Thank you.